In this work, we present PROCA, a method for place recognition under occlusion and changing appearance via disentangled representations. Place recognition is a critical and challenging task for mobile robots, aiming to retrieve an image captured at the same place as a query image from a database. Existing methods tend to fail while robots move autonomously under occlusion like cars, buses, and trucks, and changing appearance like illumination changes and seasonal variation. Because they encode the image into only one or two codes, entangling place features with appearance and occlusion features. To overcome this limitation, we propose PROCA. It is an unsupervised approach to decompose the image representation into three codes. A domain-invariant place code to describe the static scene, a domain-specific appearance code that captures appearance properties, and a domain-invariant occlusion code that encodes occlusion content. During the training, we select unpaired images from two domains. For example, the images in the blue box are with occlusion captured in spring, and those in the green box are from autumn without occlusion. We first perform a cross-domain mapping to translate the image to another domain by swapping the place codes from unpaired images. We then reconstruct the original image pair by using cross-domain mapping again to constrain the place code to be domain invariant. But as we all know, when autumn comes, trees do not always get naked. So when we translate images from autumn to spring and back to autumn, we don't know if we should generate bare trees. If we enforce the reconstructed image to be the same as the original image by cycle consistency constraint, the place codes will be entangled with appearance properties. Therefore, we encode the appearance codes to propagate and preserve them in their own domain. Similarly, where and what kind of vehicles should be on the road is uncertain. When we translate the images with occlusion to without occlusion and back, we don't know how to reconstruct the content of the vehicles. So we encode the occlusion codes to propagate and preserve them in their own domain as well. However, there is a problem with such a framework. Since the place encoder and the occlusion encoder symmetrically encode the content, the generator tends to ignore the place encoder and directly obtain all contents from the occlusion encoder to reconstruct the image, which results in the failure of feature disentanglement. To tackle this problem, we transform the original image pair by 90 clockwise rotation, and apply the cross-domain mapping to the transformed image pair. Assuming that the geometric transformation between the transferred images should be identical to the original images, and the reconstructed transformed image should be identical to the original transformed image, we propose a geometry consistency loss and a cross-cycle geometry consistency loss to further separate the place code and the occlusion code. If the generator ignores the place encoder and directly obtains all contents from the occlusion encoder to reconstruct the image, these two losses would not converge. So these two losses can ensure we disentangle the place content from the occlusion code and the place cues only come from the place code. At test time, we use the disentangled place code to retrieve an image corresponding to the same place from a pre-encoded database. We evaluate our method on the CMU Seasons dataset. Here we show some examples of matching pairs of PROCA. For each pair of images, the left is the query image under diverse conditions, while the right is the retrieved database image. As shown here, our model performs compelling place recognition under extreme occlusion and changing appearance via disentangled representations. Here we show the quantitative results under different conditions for all baselines. We report the percentage of query images correctly localized within three different pose error tolerance thresholds. Our proposed method achieves higher accuracy than all baselines in all conditions. Furthermore, for an intuitive visual experience of the feature disentanglement, we extract the codes from a sequence of images and calculate its similarity matrix, where the ground truth similarity matrix is diagonal. As shown here, the disentangled place code is significantly distinctive, thus preferable in place recognition. On the contrary, the appearance and occlusion codes are hard to distinguish among different places and thus should be decomposed from all codes. So that's it, thanks for your watching.